Hi everyone. Today we are going to talk about binary search. So binary search is an algorithm which is used to find a target element in a sorted sequence. Okay, so let's try to understand the definition. So I hope everybody must have heard about something called as linear search. Okay, let's talk first about linear search and then we can understand what are the shortcomings of linear search and why we need binary search in the first place. So linear search is nothing but, suppose if I give you a collection of integers, right? So you can store this integers might be in an array list or in a integer array. So this is a collection of numbers. You have something like this 12 and let's say 1 and then 0. And here our job is we want to find whether a particular number, let's call it as target. Okay, so this we can take from the user. Okay, and then say we want to find, let's say, the target element, let's say 4. Is this number 4 present in our collection? Okay, so let's call it A. I'm referring here as an array. So here we have an array of elements and we want to check whether the number 4 is present in this array. What is the logic or what something which comes to our mind when we hear about this question? Simple thing we could do is we can take this target and go and check each and every element present in the array. Correct? So you will go and check is 4 equal to the first element in my array? No. So let's go to the next one. So here we see that 4 is equal to the second element which is present in the array. And so we can say that we have found this target in our array. Correct? So this is what you will do. So let's assume now we can change this target value from, let's say, 4. Let's make it to 0. Okay. When the target value was equal to 4, how many times did we have to, how many elements in the array we had to check? We had to check 2 elements, right? A of 0 and A of 1. And we were able to find 4 in the second place, right? When we have target value as 0, what you're going to do in linear search, you're going to go to every element of the array, right? You're going to say, is 0 equal to 2? No. Let's move on. Is it equal to 4? No. Is it equal to 12? No. Is it equal to 1? No. Is it equal to 0? Yes. So we can say that the 0 was present in the last position of the array and we were able to find the target element, right? So when target is equal to 0, how many elements did we search? So 0, 1, 2, 3, 4. These are the indices of the array, right? So how many elements we have? We had 5 elements. We had to check or we had to compare 5 elements of the array to get whether we are able to find the target or not. Let's take another number. When your target value is equal to something around 11, correct? So to check whether this 11 is present in the array, again what we are going to do is we are going to visit every element present in the array and ask the same question, are you equal to 11? So if we will do this and we'll reach the end of the array and yet will not find the element 11 in the array, and we're going to say that the value for this is -1, where I'm saying -1 meaning that I have not found the element or the target present in my array. So -1 is just an indicator, okay, saying that whenever it's -1, it means that I have not found the target element in the array which is given to me, correct? Now from this, what we can, understand is whenever you're doing linear search, what we just did the exercise, right, where you had to find any element, you went and checked each and every array element, right? So this exercise of checking each and every element in the collection, whether it's an array or whether it's an array list, right? So when you're checking each and every, element to verify whether it is equal to the target, this is nothing but called as linear search. Okay, so the word linear here actually refers to the fact that you have to check each and every element until either the array elements are over or else you have found the target value, right? So in the worst case, you would have to check all the n elements which are present in the array. Suppose if the array has n elements, you're going to check all the n elements, and that's why how many comparisons you would need? You would need at least n comparisons, right? So the worst case time complexity, if I have to talk about, is going to be O of n. Correct? So this O of n will be the case whenever your input, okay, whatever your target value is present as the last element of the array, or else if that target value is not present in the array. In both the cases, you would run into a time complexity of O of n. Correct? What can be the best case? The best case for linear search would be if the target value which you're looking at is present in the first, at the 0th index of the element, right? In that case, you will just make one comparison, correct? So I can say something like O of 1. So we say on an average, a linear search average, or in worst case, linear search is going to take O of n time complexity, okay? Because you're going to run a for loop. I hope everybody understands what O of n means, because, I have had students facing difficulty in understanding time complexity. So just trying to, revise that here again. Whatever you have, when you say O of n, it all means that you're going to run a for loop, which is going to run for n times, and for every value, like for every value, you're going to put a if condition. Is your if is your a of I equal to the target value? If it is, then you can simply say that yes, you have found the element. But if you finish the for loop and yet you're not able to find the target value, means you have said that the value is not present in the array. Okay, so the word linear is because we have a linear time complexity. I hope that makes sense. Okay. So this is one way of finding your elements. Okay. Finding a particular target value in a collection or in a array numbers. Now, linear time complexity, right? So let's talk about another algorithm in which you can find a target value, and it is a little faster as compared to your linear search. And that what we were talking about is binary search, right? So now the word by binary, by actually means two, right? Binary, you know about binary number system, zeros and ones, right? So here we have binary search, and there's a reason why it is called binary search. We'll come to it when we look at the algorithm. But understand, whenever you have to do a search of what you're trying to search a target value in a collection of numbers or objects or anything, you want to search for a particular value, you can do so using binary search as well. But there is a main requirement of binary search, and the main requirement is that whatever collection, whatever array you have, that needs to be sorted. It needs to be sorted. Sorted as in either it can be present in ascending order, or else it has to be present in descending order. One of them, right? Either ascending or descending. So your binary search can be applied on a collection of numbers or an array only when the array is already sorted. Okay, so let's say if you want to still go ahead and apply binary search, and if your array or your collection is not sorted, please ensure that you sort it. Right? If it is an array, you can simply do using arrays.sort. This is, I'm talking specifically from Java point of view. So I can simply say arrays.sort and put the name of the array. It will sort the array in ascending order. If you have a array list, you can use collections.sort, right? It's collections.sort, and name the list array list, and this will sort your list in ascending order, provided that you have an array list of integers. Okay, I hope that makes sense. So first requirement is that the collection or your array needs to be sorted. Now we'll understand two more things. Why do we need it to be sorted? Second thing is why the word by is there in the binary search. And third thing is how it is really, efficient as compared to your linear search. All right, let's talk about that. So let's take an example here. So we have some numbers. Let's take some sorted numbers here, right? So suppose 2, 3, and let's say 4, 8, and 10. So we have around 5 numbers, 0, 1, 2, 3, 4, right? These are nothing but the indexes or the indices of your elements, array elements in Java, right? Anyway, I mean Java, C++, the concept remains the same. So the algorithm of binary search, let's talk about how the algorithm says that how can you find a target element. Let's say our target element we are trying to find is a value equal to, let's say 10. This is the value which we are trying to find. Binary search, because the array is already sorted, here we have an ascending order. Binary search says find out the middle element. Now, how do you find the middle element? Simply, if you say this is the starting point, okay, starting index, and this is your ending index. Okay, so let's have given some variable names, low and high. Okay, I'm going to find the middle element by simply doing 0 plus 4 by 2. That is nothing but the index would be 4 by 2, which is 2. So this can be the middle element. Let me say a short form mid. Okay, I'm going to make a comparison with the middle element and the target. So middle element A of mid right now is 4. Is 4 and 10, what is it? Is this value greater than, I'm going to ask a question, is this value less than, is this value greater than, or is this value equal to the target value? Target value is the value which you want to search. Okay, we have taken the middle value. Yeah, why have we taken the middle value? The intuition is because you have already sorted, you already have a sorted array. Think about this, right? The middle value is a value which is, I mean, it's like, it's standing in between, right? All the values to the left of it are all the values less than this. All the values to the right of it are the values which are greater than 4. And these values are less than or equal to 4. Correct? By asking this question, okay, this value mid right now, 4, is less than 10, right? So you tell me, if a value, the middle value is less than 10, and you have a sequence like this where all the values to the left of it are less than or equal to 4, all the values which are greater than 4 are to the right of it. The target which you're looking at is 10, and we know now that the middle element, which is 4, is less than the target value. Correct? So tell me, where should you be searching? Should you be searching in this half, or should you be searching in this half? Where will you search logically? You will definitely search in this half. Why? Because the middle element is less than target. That means our target value is greater than 4. Correct? If the target value is greater than 4, where in the part of my array will that possibility that that element exist? Obviously, the number cannot exist here, right? Because we are looking at a value which is greater than 4. Will it actually lie here? No. How can I be sure? Because the array is sorted in ascending order. In ascending order, we always write smaller elements and then we go on to the larger element, right? Now, do you understand the importance of sorting in binary search? Because we already know that the data which you're operating on is sorted, okay? So we ask a simple question that this is my middle element with whatever element you're trying to search, that's your target value. How it is in comparison with the target? It is less than, is it greater than, or is it equal to? Okay, so here if you can see that this value 4 is less than the target value, that means I am looking for a value greater than 4. So where you should be searching, you should now try to search in this half. That means I can conveniently discard this half. When I say discard this half, it does not mean you're destroying the elements from the array. No. What it really means is now my search, okay, you are looking at search, right? Initially you had to search an entire array which had 5 elements. After we did this exercise of finding a middle element and tried to ask whether your target is greater than or smaller than or equal to the middle element, we were able to say ki, okay, we do not need to search in this part of the array. We need to search only in this part, the part which is to the right of your middle element. Okay, that's what we are talking about when I'm talking about the searching space. So what I'm going to do is after 4, we had these elements 8 and 10. So let me write it here. So let's see, here we have, so here we had some numbers here, 4 was here, 8 was here, 10 was here. These numbers are still exist. What was the numbers? The numbers were 2, 3. Okay, so these are still existing, right? This was your middle element. Now where do you have to search? You have to search in this part of the array because this part is greater than 4. Our target, which we are trying to look at, is still what? Target value is still 10. If you're going to look only in this half, tell me in this particular range of the array, what is the lowest value? This. So the index is this, and this is your high index. Okay, this low and high are nothing but variables which are storing the indexes of the smallest value and the largest value in that small range in which you are trying to search. What you're trying to search? You're trying to search the target value. Okay, let's write indices here as well. 0, 1, 2, 3, and 4. Correct? Can we do the same exercise here? Yes, you can think of this. Now you have divided the entire problem into a sub-problem. Sub-problem as in you are saying that you're trying to now actually look at your, trying to find out the same problem. What is the problem you're trying to look at? To find the value 10 present in my array. So we're looking at the same thing, but now instead of searching on our 5 elements, now we are searching only on 2 elements, right? So what is happening is your possible search space has been reduced. Okay, so just by doing one simple comparison, we are able to reduce the search space. Right, so now on 2 elements, again, what we're going to do is find the middle element. To find the middle element, we can use the simple formula here. So we can say 3 plus 4 divided by 2. What is this? This is 7 by 2. So 2 into 3 is 6, right? So it is 3 point something. It's integer division. In Java, you can only take 3. So I can say the middle element here is this. Right? So what again we're going to do? This is your middle element. You are going to make a comparison with the target value. Our target value is 10. What is this? Is 8 less than, greater than target? What is it? It is less than target. That means you're still looking at values which are greater than this middle element. Okay. So if you look at the array now, 8 and 10, if you have to try to find values greater than 8 and you know that the array is sorted, where will you try to search? Obviously to the right of 8. I hope you're getting it, right? So what we'll now have now, because after you do this comparison, you know I have to look at this part of my array, right? Let's look at the part of the array. The array part which we are looking at now is only one element, correct? Let me write here, there was 8 here. Initially, what all values were there? 2, 3, 4, right? So we have 2, 3, and 4. So 10 is here. Can you see this? 10 is here. And this is only your starting and your ending of the search space, right? So you have brought down your search space only to one element, correct? And now again you will ask the same question, whether 10 is equal to my target value. Is it greater than or is it less than? What is the target value also? 10. Is it equal to? Yes. Did you find the element? Yes. What will you return? Usually in binary search or in any kind of linear searches, we try to return the index where the value is found. Okay, that is what the problem statement is actually defined in theory. So we say binary search actually returns as the index at which that particular target element we are looking at is there. Here the index is 0, 1, 2, 3, 4. So you found it at 4 index, you're going to simply return the value 4. Okay, and now I think it makes sense. I mean, I told you, suppose if my target value instead of 10, if I change it to target as 12, right? You still will come till 10 only, right? Now is 10 equal to 12? No. But number, all the elements are also over in the array. We can say that the element 12 is not present in the array. Okay, tell me index of an array, okay, or index of an array list is always positive, starts with 0 and 1, 2, 3 and so on, correct? Can an index ever be negative? No. And that is why we can sending -1. So when you do not find the particular number in your array or in your collection, we usually send -1, meaning that -1 cannot be a possible index, and it makes sense that I can use -1 saying or indicating that this value of 12 is not present in my array. If the value, for example, if its target was 10, you were able to find it at index number 4. I hope this makes sense, right? So to summarize, let's see what we have done, right? We just spoke about this in plain English, right? We not even spoke about anything, in terms of algorithm or anything. Now let's put everything together and see how you can frame this into proper algorithm. So let's say we started with these numbers, right? 2, 3, 4, 8, 10. Now from this you divided this array into 2 parts because we talked about mid, right? We said this is one space right? So 2, 3, 4 was one space. This was your mid element, right? So let me write it here. And this was your 8 and 10. You try to question the middle element. Are you equal to my target, right? Okay. If it was, in our case, the target value was 10, and because 4 was less than the target, we went ahead and solved this part of the array, which is the right hand side, which was this value. This part has value greater than 4. This value less than or equal to 4. Okay. Next part. So what is next we can do here? Let me change the color. Here what we did, we found out the middle element. So middle element here was 8 itself, right? And sorry, we had 8 itself here, and we had 10 here. One second. So we have 8 here, right? And here also we had the middle element itself is this. What about this? This middle element, is it less than or equal to or greater than target? It is less than the target. That means what part of the array you're interested in? 10. So we have only one element here. We can directly ask, is it equal to target or no? If it is equal to target, you have found the element. If it is not equal to, obviously you have not found the element. Think about this. How many steps did you take? You took this, you divided the array. This is one step, and this is the second step, and I think this is the third step, right? So around 3 to 4 steps you have taken. When you have your array elements, total values are 5, you are taking around log of n steps to find whether the target element is present in the array or no. I am saying log n not all the time. I am saying log n in the worst case. Like in our case, if you see, the target value was at the end of the array, right? So obviously we couldn't find the element until we took around 3 to 4 steps. Right? So that means if I can put this as, whenever my elements size of the array is 5, I am taking around log of n steps. Okay, if you take log of 5, you'll understand log of 5 is around 3, and that is what that many steps I have taken. Okay, that is what significance of log of n is here. Most of the people do not understand what log of n this is. Log of n, actually, for people who are from non-CS background, log of n is basically like a function, right? So you must have heard about x square. What is x square? X square is nothing but x into x. So similarly, you also have a function called log of n. It's a very mathematical thing. We do not need so much. You can simply have values. If you know value of x, you can find out the value of x square. Similarly, if you know the value of n, you can find out the value of log of n. There are tables for logarithmic where you can find the values, right? So I'm saying here, if my value of n is nothing but the size of my array. Okay, so if my size of my array is n, how many steps or how many times I need to, compare that value, compare what? The mid value to the target is, I'm saying you take around log n steps. And if you remember, time complexity is nothing but how many times a particular instructions are executed as a function of your input size. So I'm saying, as if your input size is 10, you would take around log of n step. Log of n, steps would be required. If it is 12, again log of 12. So that is what we are talking about, and that's the worst case. When in binary search, if you're applying binary search, the number of times, or the number of steps you would take to find your target will not be more than log of the size of the input. That's what we mean by time complexity of binary search being as log n. Okay, I hope this makes sense. We can take one more example, a simple one. Suppose, let's say, think about this. We have around 10 elements in the array, correct? What does binary search do? And assume that these elements are sorted. It can be sorted in ascending and descending. That does not matter. What you'll do is divide this into 5 parts, right? You ask the question to the middle element. Let's say the middle element is not, the target value. Let's say, according to our comparison, this is where we have a possibility of finding the array. So in this 5, you'll again divide this might be into a step of 3 and 2. Correct? Because it's an odd number, 3 and 2 makes more sense. So 3 and 2. So here again, let's say the array is present in, the target has a possibility of presenting in this half. What you're doing at every step, you're kind of discarding a part of the array, and you're basically narrowing down your search space. Initially, your search space. What is search space? Search space is, let me write it down. Search space is nothing but what? How many elements you have to search through. Correct? It's like, imagine, you are in a classroom. Let's say you have a classroom of, let's say, 100 students. Okay. And one of them only has the, kind of pen, you want, suppose you want some pen, and that only one of the student has it. How are you going to do it? How are you going to try to find it? One way is go to each 100 students and ask the question, do you have that pen? Right? What is that? Linear search, asking every student in the class. What is another way? You stand in front of the class, ask them. Most of the students are placed, in like rows and columns. How you sit in a typical classroom setup, and you ask, okay, tell me which half of the students are. Do the students to the left of me have the pen, or do the students from the right of me have a pen? Somebody will say yes or no, right? And you keep on dividing it until you get a pen. Similar to that, you have here also. So let's say you have 10 elements to start with. You divide it into 2 parts, 5 and 5. Let's say this part of the array has a possibility of the target. Okay. Out of this, let's say in 5 also, you again divide it. Let's say this half has the thing. Now 3 also you can divide into 2 and 1. Suppose you find the target here. How many steps have you taken? You have taken this 1 step, taken this 2 step, and taken this 3 step. So this is like log of 10. Log of 10 is less than or equal to 3. That's what I'm trying to say. Okay. I hope that makes sense, right? So basically, if I have to say if n value is 10, okay, then if I'm saying number of steps taken are log of 10, that means total number of steps are around 3, and this 3 is less than or equal to log of 10. So that is what I'm saying. And that's why I would say for binary search, take any example, the time complexity is around O of log of n. I hope this makes sense. Every time you are decreasing the search space. Okay, I hope this makes sense, right? So now let's come back to what are the advantages of binary search, right? One is very obvious. One is that if your data is sorted, correct, directly apply binary search if you're trying to find something. Why? Because log of n, this time complexity, is very, very efficient as compared to O of n, right? Log of n, this will is very, very efficient in O of n. That is one thing. Second thing is that you do not require any additional space to do your binary search, right? Did you see me taking any additional space? No. Whatever was there in the array, I have taken that space only. Yeah, you only took space in terms of that variable. What variable we created? Mid, right? And another variable low and high, right? And as you know, when you think about time complexity, we never think about individual space required for individual variables. No, because no matter what is the size of your input, you're always going to take mid and low and high, right? So even if your n size is 100, still you're going to have these three variables. If your n size is 2 or 3, you're still going to have these three variables, right? It does not change with depending on the size of your input, and that's why we do not take that in our time complexity comparison. So we can say the space required is O of 1. O of 1 meaning that it's constant. You're not taking any additional space other than what is there in the, already you would have a space for array. You're not taking anything else for processing is what you mean. Okay, but you need to bear in mind, like the most common mistakes which students do is, like, let's say they want to they get a question, right, and where they have to find out a particular target in an array or in a collection, like an array list. Now that array or array list is not sorted, so they do remember that yes, for binary search we have to actually sort this. So they will sort. Okay, happily they will sort, and then they'll apply binary search. But then they'll go and tell that the time complexity is O of log n, which is wrong. If you are going to sort it when you're writing the code, you have to take into consideration the sorting time of n log n plus the binary search of O log n, right? And then your entire code is going to be now O of n log n plus log n is going to be asymptotically O of n log n. So please make sure you bear that in mind. Second thing, ensure that you always have your whatever data you are applying binary search on is sorted. It can be in ascending order and descending order. You can change the code accordingly, but make sure that it is sorted. You cannot otherwise apply binary search on an unsorted data. It is wrong. Okay, I hope this makes sense. Now what we'll do next is, let's go to the code and see how to implement binary search, right? Actually write code for this. So binary search can be implemented in two ways. One is the recursion way, okay, and the other one is the iterative version. What is iterative version? Just a fancy name for loops, that's all. Basically the code which does not have recursion, simply using for loop or while loop. If you've written some code, that is called iterative way, and another version is recursion version. You can use whichever you like, right? Now you just have to bear in mind, if you know what recursion is, recursion itself will take some space for recursion stack, right? Because you're going to call the functions here. Function calls happen, no, f of 2, f of 1 and all. So this is going to take some space. That is called recursion stack. So recursion, if you are actually implementing binary search as recursion, okay, you have to please bear in mind that because you're using recursion, you are going to take some extra space of log n for the recursion stack. But if you're doing iterative, anyways, there is no extra space required. Okay, so please bear in mind what version you want to use. Yes, so let's go to our IntelliJ and see the different versions of binary search, right? Different ways. One is iterative, another way is a recursion one. So here if you can see, and this code, don't worry, this is on my GitHub. I'll link this GitHub in the description section. You can happily go and check the code, right? Just clone the repo and you'll be able to see the file. So here you have, I've taken a simple array, okay? I put the values here 4, 1, 3, 9 and 7, right? And as you can see, this is not sorted, right? So what I have to do, first thing though, I have to make this sorted. So let me write here arrays dot sort apply. So this is going to sort in what order? It is going to basically sort in ascending order. Now can you see I'm getting some error here, right? The reason being I have not imported. So I will import java.util.arrays. Okay, so arrays belong to the util package in Java, and just have to make sure that you are importing that, right? So arrays.sort is going to sort my array in ascending order, right? Now I'm trying to look at the target 3. So I basically want the index, if it is present, of which element? 3 element. So here I've written a function for it. So you can see the name of the function is binary search. I'm passed in the array. Obviously, I need to know starting, when you're starting to do your binary search, right? Obviously, your search space is your entire array. So your lower index is the index 0, right? Because we start indices from 0 in programming. And the higher index is the length of the array minus 1. That means if your length of the array is 4, the last index is going to be 3. So that is why a dot length minus 1. What is a dot length? It's nothing but the length is nothing but a Java function. If you know the name of the array, you can find out the length of the array by using a.length, right? What is target? Target is nothing but the value which you're trying to search, right? You can give this as variable names. You can give any variable names you like. So this is the code. Here, see what I've written is it's an iterative version. So I have first find out the middle element. Can you see this middle element? Yes. So int mid equal to low plus high minus low by 2. For now, let's leave this. Now you can just say this is high plus low by 2. We'll come to it in few minutes why I have written the way I've written. But for now, just bear in mind that it is equal to saying high plus low by 2, basically finding the middle index. Okay. If the target value is equal to the middle value, which we have a of mid, so obviously you have found the target and you can return the index. Now index is stored where? In the mid value, so return mid. As you can see, the return type of this function is also mid. Okay, I think this is very easy to understand. What is the other two conditions you can have? Either the middle value is greater than target, right? Suppose if the target value, you are, let's say we have array like this, let's say 1, 3 and then 5 and then 19, and let's say we have 30 and then we have 45, and let's say the target value we are trying to, suppose this is the values, right? So we can have somewhere around 19 as a middle element. Okay, and let's say the target value we are trying is 3. So what is happening is a of mid, let's say 19 is a middle element, so 19 is going to be greater than 3. If 19 is greater than 3, where should you search? You should obviously search in this half, 135, because there you have values less than or equal to your 19, correct? So where will you do that? How can you do that? Here, I think this is the iterative, this is the recursion version. I'm so sorry. So the recursion version, you can see I've returned binary search, okay, calling the function again, binary search a low is going to be the same, right? 1 to 5. How can you define this, the boundaries of this part of the array? This 1 is nothing but the lowest index, right? Which we also had here, correct? So I'm going to say low. But what is till where you have to search? Do you have to search till the last 45? No, we have to only go till 5. Do you know the index of 19? Yes, it is stored in mid, correct? That's what we said. So we have to go till only 1 before the mid. So it's going to be mid minus 1. I hope you got this, right? So because we said that let's say your middle value a of mid is actually what? I hope this is clear. A of mid is actually 19, correct? So the mid is actually having an index of 0, 1, 2, 3, which is 3. Yeah. Because we said the target value is less than the middle value, which is 19. We are going to search in which half? This half, right? 135. What is the, index, starting index and the ending index of this small half of a sub array? This is low. If you know the index, this is mid. What is this? Mid minus 1. So low, mid minus 1. And target, right? We're still searching this. You're going to call it again return binary search because you're doing recursion. Here I have not written any else because we do not need it, right? I hope you know this, right? Even, if this condition is not satisfied, obviously it's going to go to this condition, right? So this condition is when your middle value is less than the target. Okay, in that case, where you have to search in this half. That means what is the index you have to search from? Mid plus 1. 2 you have to go till high. So mid plus 1, 2 high and the target. So this is what we'll do. So at how many times you should keep on searching? How many times can you keep on searching? Until my low is less than or equal to high. Let's talk about this. Let's say let me just erase this part. So we are searching until low is less than or equal to high. Let's say, why do we have this? I think most of you must have figured out, but for others who have not, let's talk about this. Suppose you have a simple array like this, right? You are going to keep on dividing this into two parts, right? You say 2, 3 here, 4, and then say 5, 6 here, and then you say 5, suppose, and then 6 here. Now, suppose you are here, right? When you are here, the low and high, both are going to point to the same element. I hope you got this. Yes, think about this. We can even take it down here. Let me erase this part. See, we had here, same example, 2, 3, 5, 6, and suppose 9, right? So 0, 1, 2, 3, 4. Okay, suppose this is your low, this is your high, right? How will you find the middle? 4 plus 0 by 2, this is mid. Okay, let's go to this half. We have to find, suppose in this half. What will you do? Again, your low is this, your high is this. What is your low? Low value is 2, high value is 4. What are you going to do? 2 plus 4 by 2. What is this? 6 by 2, which is nothing but 3. So 2, 3. So what is your mid now? This value. Okay, when you are having it this value, what is going to happen? Again, you're going to ask the question, right? This is value. Let's say we have to search in this half. So what is this half? Your 2 and 3. 2 and 3 index nothing but have value 5 and 6. Correct? We have to search in this half means you're only looking at this value. So your low is also pointing to index 2 and your high is also pointing to index 2. Correct? That means what? Low and high. Let's say our target value is not equal to 5. What will you do? Depending upon whether the value of target is greater than 5 or less than 5, either you'll go to this side or either you'll go that side. Correct? Let's say the value of target which we are looking at is greater than 5. So where will you say? You would say that low should be equal to mid plus 1. right? So what will happen? Low will become 3 and high is still 2 only. We don't do anything with this. What is going to happen? Low is 3 and high is 2. Does it make sense? No. So we have to go only till low is less than or equal to high. Why equal to? Because when you have only one element left, as we saw here, the low and high both are pointing to the same index. And we also have to check that, right? Whether if it's only one value also, we have to check whether it is equal to target or no. So that's why we are going to keep on doing or calling those functions until low is less than or equal to 5. Low less than or equal to 5 means low is nothing but the index of the starting, subpart, and the high is the index of the last subpart. I hope you got this. Okay. Next is when we was talking about mid. Most of the time you will see like on a lot of sites, like Geeks for Geeks and all, you will see the finding middle element is always done like this. Mid, usually it's an integer. Int mid is equal to low plus, high minus low by 2. Okay, why do they do so? Simple reason most of you must have heard is that because to avoid overflow. What does this mean? So see, integer in any language, let's say if I'm talking about Java, an integer value has a limit up to what is the maximum value it can take. I think integer takes around, minus 2 raised to 31 to around 2 raised to 31 minus 1. There's some range for every primitive data type, right, in Java. And for other languages as well. Suppose if I had to use this formula, which we normally use, low plus high by 2, which we have even learned in maths, right? Suppose if you use this formula, imagine you are trying to add, let's say integer can go, suppose just taking an example, can go as high as 100. So think about this. Whenever you say integer, addition of two integers in Java, okay, or in any programming language, there's a limit to how big of a number it can fit, right? For example, in integer, if it is in Java, there is a limit to how big number you can fit inside it, right? I think it's around 2 raised to 31 minus 1 is what the big number you can fit. You cannot have a number greater than this. Try to fit inside an integer, it is going to overflow, right? I'm talking about this in terms of Java. For other programming languages also, it is on similar lines, okay? Now imagine, suppose you have this low value, right, and high value. Suppose they are very high. High means I can say this is 2 raised to 31 and this is also 2 raised to 31. If you're trying to add 2 raised to 31, obviously the resultant number is greater than 2 raised to 31. And this greater than 2 raised to 31 will not be able to fit into integer and you're going to get an overflow. When there is an overflow, obviously the values are going to be wrong, right? You do not have any guarantee that you're going to get a correct value. I hope you understand this, right? So to avoid overflow, what are we trying to do is we are trying to come up with use this particular formula, low plus high minus low by 2. Okay, now mathematically, let's try to get one more page blank. Yes, so mathematically low, let's take a different color here. Okay, so mathematically low plus high by 2, okay, is actually equivalent to low plus high minus low by 2. Okay, so let's understand how. Okay, so if you think about this, what is this? Mid is equal to low plus high by 2, right? Low plus high by 2. Can I write mid equal to low plus some x? Can I write this, right? The value of low is going, the middle value is from at some distance from the index low. What is low? Low index is nothing but it is, a second. Okay, so if you see, you have this low value and you have a high value, right? So your middle is this, right? So can I say mid, to reach this midpoint, it is basically low plus some value x. For example, if this low is 2 and this middle is somewhere around 4. So if I say 2 plus 2, it's going to give me 4. Okay, suppose I change it to 6. What is going to happen? 2 plus 4 is going to give me 6. So I'm writing this low plus some value x is going to give me mid, correct? So what I'm going to do is this low plus x mid. Can I substitute mid for this because I know this? So can I say low plus high divided by 2? You need to find out what is the unknown x. So can I just rewrite this as x equal to, okay, low plus high by 2. Okay, now let's erase this part. And what we're going to do is, because low plus high by 2 minus low, right? This, if it goes this side, is going to become subtraction. Addition will become subtraction, simple maths. What is this going to be? Let's club that together. Low by 2 minus low plus high by 2. Okay, so basically you have half minus 1. That is nothing but minus low by 2. This gives you plus you have high by 2. What does this is? Nothing but high minus low by 2, which is your x. We said, what is it? X is, where's the value of x? Mid is equal to low plus x, remember? So did we find the value of this? Can we write here mid equal to low plus x, right? What did we find the value of x? We found the value of x as high minus low by 2. So did we not prove it? Yes. So you can find out middle value. Either you can write this or write this. But if you write this, what happens is there's a possibility of overflow in our program. So to avoid overflow, we are going to take this. How are we avoiding overflow? See, even if you take bigger number, which we had taken, right? 2 raised to 31 and 2 raised to 31. Subtraction of bigger numbers is always a number smaller than both of them, right? If you take, obviously same is going to be 0. But let's say if I take 2 raised to 31 and 2 raised to 30, the whatever result in subtraction I get is obviously a value less than both of them. Correct? So we have a guarantee that we'll never go to overflow. I hope this is understood. So coming back to our IntelliJ, here if you see that's why we have done this low plus high minus low by 2. Actually, mathematically, it's equivalent to high plus low by 2. If you see in the code, we have this if low less than or equal to high, meaning that we are going to keep on finding and searching the value, keep on dividing our answer solution space or search space into half until we have at least one element left. If it is less than one element, means there's nothing to search. That's what we are doing this. So this is we're going to be using recursion. Okay, I hope this is very easy to understand, right? You can find this code. There's a GitHub link. You can find it now. Let's look at the iterative version for binary search. It's very easy iterative. If you understand recursion, iteration is also easy. So again, you're going to send an array. You have the low and the high, and then you have a target value which you're trying to search. Here, you're going to again have a while loop, while low less than or equal to high, meaning that you're going to keep on performing the search operation until there is at least one element present in the array. What is this? We're first finding the middle value. I hope now you can understand how you're finding the middle value, right? Low plus high minus low by 2, which is equivalent to saying low plus high by 2. If the target value and the middle value which we have found, if it is same, then obviously you can return the index of the middle value. If not, what we're checking, if the target value is less than a of mid. Okay, if the value of target is less than a of mid, then where are we trying to find out the elements? We're trying to find out the elements in the value smaller than mid, right? Smaller than mid means what we need to do is your high is going to get reduced. Okay, otherwise your else is going to become plus plus. So here we can simply say your high is nothing but mid minus 1. Otherwise your low is what? Equal to mid plus 1. Okay, very similar to what we have done here, right? Your value, whenever it was, if the middle value is greater than the target, we said it is from low to mid minus 1. So the middle value is greater than the target, which is going from mid plus 1 to high, right? Similar to this. If a of mid is greater than target, if a of mid, here it is, if a of mid is greater than the target value, you are going from low to mid minus 1. So here also you have low to mid minus 1. Otherwise it is mid plus 1 to high. So otherwise it is mid plus 1 to high. We are not changing anything to high, means it's mid plus 1 to high. So this is going to be a simple for loop. If within this while loop we are not able to find, if it does not return the value, so obviously we are going to return minus 1, saying that we did not find the target element which we are looking at. Okay, so I hope this works. Let's just run this. Yes, so index of 3 is 1. If you see, if you have to first sort this, right? So after sorting, the array looks like this: 1, 3, 4, 9 and 7, right? So the index in the sorted part is going to be 0, 1. So the index of 3 is 1, and that's why it is returned to us. Index of 3 is 1. Okay, let's take simple example and try to dry run binary search code, the recursive version, right? Usually I hear from students that they get very confused in how recursion functions are called, right? So let's try to even understand that and dry run a binary search on an example. So let's say we have an array. So the numbers are 2, let's say 4, okay, 10 and then 15. Okay, so what are going to be indexes for this? Well, let's say one more number, 18. So indices are going to be 0, 1, 2, 3 and 4. Okay, and the target value which we are looking at is, suppose, say 15. Yeah. So how would the recursive version for binary search work? Let's call that function as binary search. You're going to pass in the value of a. Okay, then you're going to pass in the value of the low index. Low index is going to be 0, high index is going to be 4, and the target value 15. You're going to calculate the middle value, right? Middle value is going to be 0 plus 4 by 2, which is nothing but 2. So a of mid is nothing but 10. Compare 10 and 15. 10 is less than 15. So where should you go? You should search in this half. Correct? If you have to search in this half, what should be your new value of low? Low should basically be mid plus 1. Do you have to change anything in high? No. So what is the next function call you make? Binary search of a. Low should be mid plus 1. What is a mid? Mid is nothing but 2. 2 plus 1 is what? 3. So it's starting from here. 3 to what? High is 4. And the target is 15. Again, we're going to calculate what? The value of mid. What is the value of mid now? For this function call, the value of mid is 3 plus 4 by 2. This is nothing but 7 by 2, which is equal to 3 because you're taking integer division. What is a of mid? That is a of 3. I think a of 3 is 15. Yes? Okay. Is this the value equal to our target value? Yes. From here, what will you write? You will simply return the mid. What is mid here? Mid value here is, where is it? It's 3. Okay, so please pay attention. How does it return, right? Because usually people do have doubts here. So you're going to say return mid. Okay, whom it is going to return to the caller. Who was this person's caller? This guy was its caller. What is it going to return? The value mid. What is the value mid here? Value mid is equal to 3. So what is this going to return? This is an actual function call, right? This must have been done from some main function, and you will have a value stored here, right? So integer index. So this index, whatever you have, will have a value what? 3, which is nothing but the index of our target. Okay, can you see this? So if you see, though we have around 5 elements, we could finish this searching of our target in just 2 function calls, right? So when we say log of n, it's a worst case scenario. So in worst case, your function calls won't be greater than log n. That's what we mean. Yes. Another thing, I hope you've understood this when it comes to binary search, right? So just go to description. You can suggest me if you want me to make videos on any specific topics. Yes, and you can even join our Telegram channel. It's all free. So we can have a small community. You can ask your doubts. We can have a nice discussion. Yes. So just share and like this tutorial if you enjoyed it. Bye.